Hello everyone, my name is Sophie. I live in Ontario. I was born in Southern Ontario and then I moved to Northern Ontario to study geology. I did both my undergrad and my master's at Lakehead University, both with Philip Freilich. I suspect some of you probably know him. And I picked Snowball Incident purely because I thought it was interesting. Since graduating, I've worked in gold exploration and in gold mining in Northern Ontario. And then very recently, I started working for the Ontario Geological Survey here in Ontario. And that was just earlier this year, I made that transition. So this talk is going to be a mixture of what we published in our article. And I believe that article was published late last year. And it'll be quite a bit of stuff from my thesis that didn't end up in the publication, but I really liked a lot of the sedimentology that we looked at, and it didn't really get to end up in the publication, so I'm going to cover quite a bit of that. So that's just a little bit of backstory about me, and I just want to say thank you very much for having me speak to you guys today. I haven't really gotten to talk about this research too much since I graduated, and it is pretty interesting, and hopefully you will all find the same. I know there's quite a few experts in the so-called room tonight, or I guess this afternoon, depending on where you are. But hopefully I've sort of tailored this talk to be at a level that everyone can kind of follow along with and understand. So I've titled this talk after the name of the paper that we published, and that was Earth's First Snowball Event. Evidence from the early Paleoproterozoic Huronian supergroup. Like I said before, this was actually my master's research, so this is a project that is the culmination of over 2 years of work. We did quite a bit of field work, and it concerns, as we know, an ancient glacial cycle. So for those that might not have as strong of a background in geology, when we talk about the Proterozoic was an eon that spanned over 2 billion years of Earth's time, from approximately 2.5 billion years ago, all the way up to about 542 million years ago. And what's pretty interesting about the Proterozoic eon was that it was actually marked by several glacial cycles at the beginning and at the end. So what I'm going to be talking about today is one of the glacial cycles that occurred at the beginning of the Proterozoic eon, so that's why we call it the Paleoproterozoic. And then the glacial cycles that are much more well known and much more understood occurred at the end of the Proterozoic, the Neoproterozoic. And probably quite a large part of that is because those deposits are much more ubiquitous and well preserved, and that's because almost 2 billion years between these deposits is a pretty significant period of time. And we just really don't have nearly as much of the rock record preserved from the Paleoproterozoic. So why do we call it a snowball Earth event, though? It is believed that during these events, we actually had these large continental ice sheets that are theorized to have extended to low latitudes. And I'm not sure if he's here, but Kirschvink in 1992 was the one that came up with this name of snowball Earth. But it was an idea that people sort of knew about before then, but that's when it really came to light. He put a name to it. And this is a really, really highly researched and debated topic today. It's pretty interesting. So I'm going to begin by giving quite a bit of background on snowball Earth theory. In particular, what we think the driving mechanisms were for the Paleoproterozoic snowball Earth events. And that's just so that everybody is hopefully on the same page again. I think this is a mixed group with different levels of knowledge on this topic. And then I'm going to go quite a bit into the sedimentology. That's the part that I find really interesting. We got to see, like I said, a lot of really cool outcrops in the field during my fieldwork. And then I'll talk about a lot more of some of the more interesting results that we got from our geochemistry and our isotopic studies. And this is where we sort of drew a lot of our conclusions from in the paper that we published. So let me talk a little bit about snowball Earth theory. So what creates a snowball Earth event? There are many possible triggering mechanisms that have been come up with. Some of them include eruptions of supervolcanoes in the past. So if you would get a lot of volcanic eruptions, what would happen is that could put a lot of ash into the atmosphere, which would of course have a net cooling effect on the planet. One other possible idea is that you could get a reduction in the atmospheric concentration of certain greenhouse gases, such as methane or carbon dioxide. And as I'll explain in a little bit here, this is actually potentially the driving mechanism behind the Snowball Earth event or potential Snowball Earth event that we studied in my master's research. Some other ideas that have been thrown out there are changes in solar energy output through time, or even possibly changes in Earth's orbit. So there's a bunch of different ideas for what could be a trigger for a Snowball Earth event. But basically, once the planet starts cooling, of course, you end up with a lot of positive feedback events, which continue that cooling process. And then you end up with a planet that has a really, really high albedo, so you're not getting a lot of warmth eventually coming down to the surface and staying there. So what happens is that your planet completely freezes over, or maybe almost completely freezes over. Some folks think that ice cover was not necessarily global. That's known as a slush ball Earth event. But anyways, you get a lot of ice cover. And then what would happen is that these icehouse conditions would prevail. But if you have global ice cover, you essentially get a decoupling between the atmosphere and the ocean. And you just get a buildup of atmospheric CO2 through volcanic outgassing. Eventually, it's hypothesized that the CO2 outgassed by these volcanoes would build up to a certain point in the atmosphere that it would actually sort of trigger a warming. And then you get this runaway greenhouse effect, and that would melt the snowball Earth. So what happens is that when the ice melts and the atmosphere regains contact with the ocean, you get this sort of re-equilibration with the ocean and the atmosphere. And the atmosphere at this time has really high CO2. And this re-equilibration would supposedly or theoretically drive precipitation of carbonates. So carbonates are a precipitate mineral. They can be precipitated either organically or inorganically. And they form these deposits that are ubiquitous above these ancient glacial deposits, and they've been termed cap carbonates. So these cap carbonates, because we see them above all of these glacial deposits, we think it tells us something very specific about the atmosphere during these very unusual climatic periods in Earth's history. So the cap carbonates are a critical component of the theory, and we see them uniformly over these Neoproterozoic or the much younger glacial deposits. And they're very similar in terms of their stratigraphy and in terms of their different facies. And so I would say that really what we were trying to do with my study was not necessarily to prove per se that what we had was a snowball Earth event, but what I was really trying to do was to look at the similarities or differences between these deposits, because they're much more well-known, and these much older glacial deposits and potential cap carbonate that we see preserved in the Paleoproterozoic. So in talking about our specific much earlier glacial deposits, there are actually 3 full glacial cycles that are preserved within the Paleoproterozoic Huronian supergroup. And the Bruce glacial cycle, which is the one that we're talking about today and the one that I did my research on, the Bruce glacial cycle is actually the only cycle within the 3 that has an overlying cap carbonate deposit. So that in and of itself tells us that there was just something very unique about the environment at this time. And what we're trying to parse out is what was different and how similar was it to the Neoproterozoic cap carbonates. So there's a lot of opposing theories. I think Hoffman is sitting in the group tonight, but he's also done some work on the Bruce Formation and the Bruce glacial cycle. There are some folks that believe that the Huronian glaciation event was synchronous all over the world. There are other researchers that don't believe that that has been proven yet, But I think most folks generally agree that the fact that the Bruce Formation has a well-developed post-glacial cap carbonate that has, as we're going to see tonight, some interesting similarities to the Neoproterozoic cap carbonates tells us that there's definitely something unique going on with the Bruce glacial cycle. So remember I mentioned before that there are these different triggers for a glacial event. And the Paleoproterozoic trigger, what we think is that it has to do with actually those changes in atmospheric conditions. So let's go to the next slide. There's a period of time in Earth history referred to as the Great Oxidation Event. So prior to the rise of cyanobacteria or oxygen-producing bacteria, Earth actually didn't really have a lot of free oxygen in its atmosphere. Actually, at this time, 2.3 billion years ago or so, Earth looked quite a bit different, right? We don't have any land plants. Life at this time consists of bacteria. And it is believed that actually Earth probably looked maybe quite a bit like Mars in that its atmosphere would have appeared red from space. And that's because the Earth at this time had a lot of methane in its atmosphere. And what happened around this time is that we get an increase in oxygen production by cyanobacteria. Now, as you all know, methane is a really strong greenhouse gas. But when methane meets free oxygen in the atmosphere, it actually forms CO2 and H2O. Now, CO2 or carbon dioxide is also a greenhouse gas, but it's actually not as strong of a greenhouse gas as methane. So we believe that this reaction actually created a global net cooling effect. And it is believed that this global net cooling effect was the trigger for this early Paleoproterozoic possible snowball Earth event. And we have some really, really strong, really cool evidence for why we think this happens around this time. And that is that we have this signal in the rocks. And this is kind of a mouthful, but basically what we're talking about here is fractionation of sulfur isotopes. Just again, for some people that might not have worked with isotopes very recently, isotopes are just atoms that have the same number of protons and electrons, but they have a different number of neutrons, and therefore they can have different physical properties. So sulfur is one of those. It has a 32 sulfur isotope, and that's the most abundant, but it also has more rare isotopes of 33, 34, and 36 sulfur. And the relative abundance of isotopes in geological materials can be affected by various different processes. It can be geological, biological, hydrological. But what we noticed is that prior to atmospheric oxygenation, there actually wasn't really a mechanism for isotopic fractionation of sulfur isotopes based on their mass in both sulfate and sulfide minerals. Again, these are just minerals that have sulfur within them. So what you can see on the left side of the diagram here, hopefully you guys can see that, is that we just get a large spread. This is the delta 33 sulfur. This is just a value that basically tells us what the ratio is between that really common 32 sulfur isotope and the less common 33 sulfur isotope is. So you can see that prior to about 2.3 billion years ago, we see this really large spread in the values, and then all of a sudden that value remains consistent all the way up to modern day. And why do we think that is? Well, the really cool thing is that the only known fractionation mechanism that is consistent with the data on all four sulfur isotopes involves basically atmospheric photochemical reactions, such as SO2 photolysis. And this necessitates having free oxygen in the atmosphere. So basically seeing a signal like this is telling us that we went from having insignificant amounts of oxygen in the atmosphere to some significant amount of oxygen in the atmosphere. So again, pretty good evidence that the Great Oxidation Event, or at least some sort of an increase in oxygen in the atmosphere, occurred right at the time that we're seeing the Bruce glacial cycle. So the purpose of my study was to summarize the stratigraphy of the Bruce glacial cycle. And this included the geochemistry and the isotopic composition of the Espanola Formation. The Espanola Formation is the cap carbonate that overlies the Bruce glacial deposits. We wanted to be able to discuss what we thought the depositional environment of the Bruce glacial event was, and then hopefully to get some sort of an indication of what the source of the carbonate fraction was in the Espanola Formation. One thing I should mention is that we see a lot more evidence for biological precipitation of cap carbonates in the Neoproterozoic. I didn't really see a lot of that in the Espanola Formation, but I know Paul Hoffman has mentioned before that he has seen some stromatolites in, I believe it was the Elliott Lake area. So there is some indication that we have biological precipitation, but it does appear that most of the carbonate fraction in the Espanola Formation was precipitated inorganically. And then to that end, what we want to try and decide or try and uncover is if the Espanola Formation was deposited by similar processes and maybe under similar conditions to the later Neoproterozoic counterparts or the Neoproterozoic cap carbonates. So there's been some previously completed geochemical and isotopic investigations. What we did here really added on to work that was done previously. And as you'll see, I did use some work that was done previously to draw some conclusions with the new data that we collected. So what's the area we're talking about here? Modern day, the Huronian supergroup outcrops along the north shore of Lake Huron. This is an inset that shows where the Great Lakes are located in Ontario, and Lake Huron is sort of the middle Great Lake, I would say. And our map area occurs along the North Shore, and it's quite a large geographical extent. I would say it ranges from about Sault Ste. Marie to east of Sudbury. It's probably at least 200 kilometers east to west. So there's a lot of outcrop exposure. And then on top of a lot of outcrop mapping, we also did a little bit of logging of drill core from the area. So there was holes drilled in the Elliott Lake area. Elliott Lake is a historical uranium mining town in Ontario. So there was some exploration activity in the area. So we were lucky enough to get our hands on some drill cores that had intersected the sediments of interest. So we did some drill core logging and a lot of outcrop mapping. I think it was the summer of 2015. We probably spent about 2 straight months in the field living out of my car. So we got a lot of field work done. And the Huronian supergroup itself is a pretty thick sedimentary package. It ranges from about 10 to 12 kilometers thick. The Bruce glacial cycle constitutes sort of the Quirk Lake group, which is, again, like I said, the second of 3 glacial cycles preserved within the Huronian supergroup. Now there is some ongoing debate about the depositional environment in terms of where it was located, either if it was on a continental shelf or in a more isolated rift basin. I tend to agree with the earlier rift-drift transition. As you can see at the bottom there, we have the Thessalon Formation. This is some of the only volcanics that we see within the Huronian supergroup. And that is where Hoffman in his 2013 paper delineated that the rift-drift transition probably occurred at the base of the Matinenda Formation. So I do believe that the Bruce glacial cycle was deposited in probably a more open shelf environment. Reasons why are that we do see a lot of preservation of strong tidal activity. As well, we did a lot of paleocurrent work. Paleocurrent just means basically looking at the direction the water was moving, and you can sort of reconstruct which way the water was moving at that time. And what happens is that in a more active rift basin, you get this upwelling of hot mantle, and it causes the rift arms to sort of slope away from the center of the rift. And that would mean that our paleocurrents would show that our rivers and stuff are moving sediment away from the center of the rift, but we actually see the opposite in the Bruce glacial deposits and in the Serpent Formation and the Mississagi. So it's suggesting to us that our material is moving towards probably what was at that time a mostly open continental margin. So I'm going to talk about the Mississagi Formation. This is the pre-glacial environment. It was important to us to be able to reconstruct what the environment looked like prior to ice advance. And then the Bruce is the actual glacial deposits. The Espanola Formation that directly overlies the Bruce, that's the formation that contains our cap carbonate. And then the Espanola Formation grades upwards into the Serpent Formation, which is again a predominantly sandstone sequence. So we have our pre-glacial, we have our glacial, and we have our post-glacial environment. So let's begin with the pre-glacial, the Mississagi Formation. So this is the uppermost formation of the Hugh Lake group. It's dominantly sandstone, consisting of kind of like medium to coarse grained sandstones, feldspathic aeronites with quartz aeronites. We do get some accessory lithologies, including some conglomerates, some argillaceous sandstones, which just basically means like silty sandstones, and argillite or siltstones. And we wanted to study the Upper Mississagi Formation to essentially determine what the, like I said, the periglacial environment was prior to the heralding of the Bruce ice sheet. And the Upper Mississagi Formation is dominated by two major lithofacies associations. And this is based on the stratigraphic trends that we observed in outcrop. The Mississagi Formation was really well preserved along the north shore of Lake Huron, where we had these large flat-lying wave-swept outcrops, and we were able to see pretty continuous stratigraphy. And what we noted was that we get predominantly these really large-scale planar cross-stratified units. That's the most common unit we recognized. And then this was followed closely by medium and small scale trough and planar cross-stratified units. So that picture on the lower right is actually, if you can see it, it's a tiny little trough that's very well preserved. And then the picture on the upper left, you can see a large scale planar cross-stratified unit. And then the top has become really contorted by presumably some sort of different current direction. So the majority of the Upper Mississagi Formation is interpreted to represent a distal braided fluvial system. Braided fluvial systems are really common around this time because, again, we don't have any land vegetation. So a lot of the fluvial systems were higher energy. We don't have any of that vegetative binding. So we do typically see braided fluvial environments. And this was supported by, like I said, we have paleocurrent data, which shows predominantly unidirectional paleocurrents. And then directly below the contact with the overlying Bruce glacial deposits, we see this interesting transition. And what we get is basically a decrease in sorting, and we see an increase in grain size. So from A, B, C, D, these are some thin sections that we took going from the Upper Mississagi just into the base of the Bruce Formation. And you can see that, you know, the size of the grains really changes dramatically as we move up into the Bruce, and we see just less sorting. We see a lot of finer and coarser material. So in almost all places, we see quite a sharp contact between the Bruce and the underlying Mississagi Formation. That yellow arrow in that image there just shows the overlying glacial deposits. We refer to them as diamictites. They're basically look like conglomerates, but they're deposited through ice processes. And it overlies the sandstones of the Mississagi Formation. So a very sharp contact you can see here. We do also see in some places, as well as the sharp to slightly gradational contact, that we do see an uptake of sands from the Upper Mississagi into the basal Bruce Formation. And all of this indicates to us that the Bruce Formation was likely grounded as it moved into the basin, and that it really eroded some of these unconsolidated sands in many parts of the basin at the time of advancement. So then we move into the overlying Bruce Formation. These are our glacial deposits. The Bruce Formation itself consists predominantly of this gray, very massive looking diamictite or conglomerate. You can see that image here on the left. This is quite typically what the Bruce Formation looks like in outcrop. And then here's an image of the Bruce Formation. This is, again, closer to Lake Huron along the coast there. You can see this sort of little window bed, and then you can see this drop zone that's actually sort of distorted the bedding underneath it. So because the predominant facies type in the Bruce Formation is a massive diamictite with very much lesser laminated to weakly laminated diamictite, we interpret the Bruce Formation to have been deposited largely subaqueously. So while the Bruce ice sheet probably was grounded as it entered the basin, it likely delaminated from its bed pretty rapidly. That can happen because ice sheets are very, very heavy and you get denudation of the landmass. But of course, ice sheets themselves are still buoyant, so at a certain point, the ice sheet becomes delaminated from its bed, and then most of the sediments look like they were probably deposited via an overlying floating ice sheet. So then we move into the Espanola Formation, and this is the beginning of our post-glacial deposit. The Espanola Formation, in most places that I saw it, is separated by the Bruce glacial diamictites by this. It's usually about 0.5 to 3 meters thick. It's a very finely laminated siltstone unit. I've interpreted this to represent probably something akin to a modern day Loess deposit or a rainout deposit that would have formed, a fine material rainout deposit that would have formed after the rapid retreat of the Bruce ice sheet. And the Espanola Formation itself into the overlying lower Serpent Formation is interpreted to represent a broadly shallowing upward sequence from this distal shelf environment that we now find ourselves in to a nearshore, more high energy environment. So the image on the upper left shows a laminated carbonate deposit, and this is pretty commonly what the Espanola Formation looks like, the lower Espanola Formation looks like in sort of the Elliott Lake area in Ontario. And you can see the white stuff is actually our very massive calcite precipitate. And then those fine gray beds that are kind of swirly in some places, those are very thin silty beds between them. And then in the lower right is an interformational conglomerate bed. And this is in the more upper portions of the Espanola Formation. And it's stained a little bit red because it's actually dolomitic, so it's got a little bit more magnesium and iron in it. So when it weathers, it has a red look like that. So the sediments of the lower Espanola Formation are dominated by sort of variably contorted, parallel laminated beds to graded beds, while the upper sediments are dominated by ripple lamination, hummocky cross stratification, which is just this really unique deposit that we get in very specific places by storm activity. And then we get a lot more cross bedding and interformational conglomerates. And this overall trend indicates a shift again from a quiet, deeper water environment where we're primarily having deposition through rainout or mass movement. And then we move to a shallower and higher energy nearshore environment where we get fluctuating influence by wave, tide, and storm activity. And then we see that trend continue as we move into the overlying Serpent Formation. So the Serpent Formation begins sort of in a more nearshore environment, and that moves into actually back into a deltaic environment near the top. So the Serpent Formation is the third and the final formation of the Cork Lake group. The Serpent Formation is predominantly a sandstone sequence, but especially where it grades out of the Espanola Formation, we see a lot more minor shale, siltstone, carbonate, and conglomerate. And this transition is very, very gradational, where you basically just start to see a loss of the silty limestones and the siltstones and move into more sandstone beds. So we interpret this transition zone to represent a shift from that wave and tidal influenced nearshore environment into, again, much more of a deltaic environment. So what you see here on the slide is we've got some images that we took when we did crop mapping along the North Shore of Lake Huron. Here's a large scale planar cross stratified bed. And then this is a little wavy laminated bed. You can see the lighter stuff here is coarser grained, and this darker layer here is finer grained. So what we've interpreted is that this represents sort of a near shore shelf that's influenced by a lot of tidal activity. And we see that represented in the paleocurrents. So these are Rose diagrams. As you can see, they've got a compass on them. And each of these little red marks indicates a measurement that we took of a paleocurrent direction. And what you see in the lower stratigraphy of the Serpent Formation is that we get this really strong bimodality in the paleocurrent direction, and that tells us that we've got a tidal influenced environment. And then as we begin to move up through stratigraphy, we really lose that bimodality and we begin to move into a more unidirectional current that indicates again that we're into a more deltaic fluvial influenced environment. So that's sort of the very quick and dirty on the Bruce glacial cycle in terms of its sedimentology. Now I'm going to talk a little bit about some of the really interesting results that we got about the geochemistry. And again, this is some of the stuff that went into the paper that was published. So I'll talk mostly about sampling that we did in one of the drill holes that we logged. And again, that's because we just had really good control on where we were in the stratigraphy, and being able to sample the drill core also gave us a really good chance to be able to look at the systematic upwards trends. So drill hole E150-2 had this one really cool unit right at the base of the Espanola Formation, and sort of right in that contact zone between the Espanola and the Bruce Formation, where we had these carbonate-rich beds. So those sort of orangey beige beds are actually layers that are carbonate-rich. And then what you can see here is this sort of quartz pebble that has been deposited and distorted this layering. And this is what we call a drop stone. And this is very unique to glacial environments because you get drop stones that are being deposited into the sediment via an overlying ice sheet that's melting. So this is just a really cool indicator that we actually started potentially seeing some of the calcite or the carbonates being precipitated really right at the end of the Ice Age. So I'm going to talk about sort of what we saw in the lower stratigraphy, where we got some pretty interesting results in the red box. And then I'll talk about what's in the yellow box above. And I'm going to talk about the delta 13 carbon. So again, this is an isotopic trend that we're looking at. And this is between 12 carbon, which is the common isotope, and 13 carbon. And then I'm going to talk about these rare element plots. So rare elements are elements that are just that they're pretty rare, but they exist sort of uniformly in a lot of rocks, and they behave very similarly typically. So whenever we see small differences in them, they can usually tell us something significant about the environment because they quite commonly behave so similarly. So I'm going to talk about the lowermost stratigraphy. There we go. So this is the lower half of our stratigraphic section. We have a very simplified stratigraphic section. This is about 200 meters that we logged. And each of these little dots represents one of the samples that we took. So these little red dots in here are actually from that really interesting, unique dropstone unit that I showed you in the last image. And what was really cool about this unit was that we received really, really interesting geochemical signatures. So firstly, it had a very negative delta 13 carbon value in comparison to the other samples that we got. And this delta 13 carbon value hasn't been noted before in the Espanola Formation, but it's on the same order of magnitude as some of the very negative delta 13 carbon values that were produced from Neoproterozoic cap carbonates. And then secondly, in these rare earth element diagrams, as you can see in the red here, all these samples that are from that unique unit, we get this dip in the europium. So europium is unique from the other rare earth elements in that it can exist in a 3+ or a 2+ valence state. For those of you that might not remember, valence state just means basically how many electrons it's missing in its outer shell. and that basically governs or determines what kind of interactions it's going to have with other ions in the water column, or even if it's within a mineral. So what we think is happening here potentially is that europium is basically being remobilized. So we potentially had a highly reducing fluid that caused the europium to go from a 3+ state to a 2+ state, and that would that would cause the europium to become soluble and essentially remove it. And that is why we think we might be seeing this sort of negative europium anomaly. And one reason why we think that is because a mechanism for producing both these really negative delta 13 carbon values and these negative europium anomalies is through a methane seepage influence. So I'll talk about this a little bit more later, but basically, even what's happening in the modern day as we're sort of coming out of our last ice age, you get this melting of these frozen methyl hydrates. And as they melt, you get this sort of methane seepage influence, which could cause highly reducing influence in sort of these subsurface sediments and the bottom waters. And it could also drive precipitation of these carbonates in these environments, and could also be potentially a driving mechanism for some of the precipitation of the carbonate fraction. And that's why we might be seeing this negative delta 13 carbon signature as well as this negative europium anomaly. So then as we begin moving up through the stratigraphy, we start seeing a trend to more of this, what I've called like a hat-like pattern. And I'll take you to the next slide where we can see that more. So we move into what obviously looks like a very different rare earth element pattern. We've lost that negative europium value. And you can see that the delta 13 carbon values have changed dramatically as well. So I'll talk a little bit about the rare earth element patterns. Like I've said, I called it like a hat-shaped appearance. So rare earth elements trend from the light rare earth elements to the heavy rare earth elements. And light rare earth elements and heavy rare earth elements behave a little bit differently depending on the environment. So typically in seawater, you get a light rare earth element depletion, but you can get more of a middle to heavy rare earth element enrichment in riverine waters. So my hypothesis for why we're seeing these patterns is that it's probably some sort of like a mixing influence on the geochemistry between these sort of like continental margin sediments with these terrigenous inputs, but we're also seeing marine influence. So it's probably some sort of a mixture between all of these different influences that are going on. And again, that's kind of also supported by the fact that we know we're in a nearshore environment where we're probably going to be having multiple inputs on the geochemistry. So we do see, however, this sort of very consistent and gradual upwards trend in the delta 13 carbon values. And you can see that it trends, so this is from -5 to 0. You can see that it trends from about -4 to about -2.5. So I thought that was kind of interesting, and I went back and looked at geochemistry that had been done previously, and what I found was Andre Becker in 2005 had done systematic sampling of one of those other drill holes that I pointed out. And while he didn't really discuss it in his paper, I kind of noticed that it does look like there's a very similar trend here in the upper stratigraphy, where the values range from about -4 all the way up to -2. So that looked to me to be a pretty consistent trend between the two. And again, while he doesn't discuss it in his paper, it is noted that this delta 13 carbon trend is noted in neoproterozoic carbonate platforms, where we see more negative values on the slope, and then these increase across the shelf as you move closer to the shoreline. And part of that is because as we come out of our ice event, we begin to see changes in our ocean water, and we get this destratification and upwelling of delta 13 carbon depleted waters in the aftermath of the glacial event. And it is believed that it is this that is sort of influencing this overall trend that we're seeing. And then as we're moving away from our more marine influence to our more river influence in our overlying serpent formation, we're sort of losing more of that oceanic signature. So that's potentially what we could be seeing in our deposits. And again, this is noted in the Neoproterozoic cap carbonate. So that's kind of cool that we're seeing similar patterns between the two. One more thing that we looked at that kind of supports this idea that we've got freshwater and seawater influence going on is the yttrium-holmium ratio. So again, these are two elements that typically show similar values depending on what sort of environment and what sort of influences you have. So the yttrium-holmium ratio of the Espanola Formation carbonates came out pretty varied. But within modern seawater, we tend to see values of about 54 for the yttrium-holmium ratio. But our chondrites and our clastic sediments typically show values that are more around 28. So what we think is that this is also supporting basically a mixing between both freshwater, which is our clastic sediments that are coming in with our terrigenous material, and a mixture between that and our seawater influence. So all of these little indicators are pointing towards basically this idea that we've got freshwater and seawater influence that is potentially giving us these types of signatures. So I'll just go into a little bit more sort of what we think the source of the carbonate fraction is in the Espanola Formation. Again, we think that we get this releasing of CO2 from warming seawaters. This is also sort of in conjunction with an increased weather rate that we would get at the end of an ice age. And then we get this high input of glacial meltwaters that are carrying these cations. And then this increases our alkalinity and drives precipitation. And precipitation could furthermore be supported by gas hydrate destabilization. Remember I said melting of methyl hydrates is a process that's still going on today. So here's just a cool image of the seafloor. And what you see in the green there is actually these methyl hydrates on the subsea floor that are melting today. And this could be a mechanism that could be driving some of the precipitation of the carbonates within the Espanola Formation. Now, methyl hydrates typically have very, very negative delta 13 carbon values, like on Northern more negative than what we saw in my study. So if there is influence by methane release, it's probably diluted. But again, it could have been a factor in some of the precipitation of our carbonates. So I'll just jump off with a conclusion here. The Bruce glacial event preserves a sequence of ice override by a grounded glacier. And this is followed by a regressive sequence that we see from a more offshore to nearshore environment. And then the Espanola Formation, which overlies our glacial deposits, we were able to pull apart a couple really interesting results from the geochemistry. And that is we get this upper stratigraphy with a gradual increase in delta 13 carbon values from approximately -4 to -2.5. We think we see this in some of the other drill holes that were logged, and this is something that is seen in Neoproterozoic cap carbonates, so that's a consistent feature. And then we do get this really interesting laminated dropstone lithophases association, which I've called that unit with the little dropstone. You can see that's displacing the lamination. And this unit had really anomalously low delta 13 carbon values of about -10. It had those really distinct rare element patterns with the negative European anomaly. And this anomalously low value is on the same order of magnitude as sort of the most anomalously low values we see in the Neoproterozoic. I believe it's called the Wakom-Sharana anomaly. I think I might be butchering that. But in conclusion, was the Espanola Formation deposited by similar processes and under similar conditions to its later Neoproterozoic counterparts? I do think that some of the geochemistry indicates that there's probably some similarities in terms of drivers of precipitation, but you'll have to make your own mind up on whether or not you believe that. So thank you very much for listening. I hope you enjoyed my talk, and I hope it was easy enough to follow along with. And thank you.
That is really terrific. Thank you so much, Sophie. That's really well presented, and I'm just blown away, and I've got a million questions, but we have some really good questions already. And
Okay.
and Marsh started with a question, but I'm trying to find all the questions. And also I would like, because we have an author that you cited as part of this.
Yeah.
Paul, before we lose you, I suspect you'll stick around, but would you like to ask any questions to Sophie or comment about what she cited about your work? And thank you. I'm not sure. Is Paul Hoffman still there? He might have had to leave. So I don't see a.
Let's hear the general questions first.
Okay, great.
Oh, okay.
All right, I'm trying to pull up the questions. Thanks, Paul. Marsha, you had the first question. So
there was one before me, actually, from Barry Goldstein. Unfortunately, he's had to leave.
Okay. I'm trying to find where these questions are, and on my screen,
they're in the chat.
Yeah, and I pull it up and I just get a gray screen. Okay, finally it came up. Okay, it just took a while. Great. Let's get down to Barry. You can ask yourself, but Barry asked, do you see striations or oriental pebble fabrics? Sophie?
No, unfortunately, I myself was not able to find anything that I thought looked like a striation. Yeah. And that was partially part of the reason why I thought it was a lot of subaqueous deposition, because we just don't see a lot of evidence for a grounded ice sheet.
Okay. Marsha, why don't you just ask your question?
Okay, well, you mentioned that cap carbonates being dolomites, and I think the cap carbonates that we saw in British Columbia tended to be dolomitic, and I'm wondering if that's more commonly the case for these cap carbonates. And this may be a question more for Paul, if he's still with us. Yeah, there you go, Paul.
Yep.
Do either of you have an opinion on that?
Yes, it is typically dolomites in the Neoproterozoic cap carbonates. Yeah.
Okay.
Well, this older cryogenian glaciation, the Sturdian, that cap carbonate is usually limestone. But the Marinoan one, the younger one, the cap at least begins with dolomite typically.
Okay. I'm wondering if there's anything to be, learned about how dolomites form from this, but maybe not. I mean, they're still a bit mysterious.
Well, sulfate in seawater is a dolomite inhibitor, and there probably was little sulfate in the immediate post-snowball meltwater, or for that matter, in the residual brine.
Okay, well, that would make sense.
Sulfate increased, of course, due to strong weathering in the aftermath, but in the immediate, probably sulfate was low, so that should favor dolomite. But if, on the other hand, there was abundant sulfate in the water due to oxidative weathering, then that might have inhibited sulfate. Also, I would say that deeper water deposits in the Neoproterozoic tend to be more often limestone. And I think dolomite is favored in shallower water environments, and also perhaps where the accumulation rates are slower.
Okay, that makes sense.
Yeah, that's a good point, Paul. And one of the other reasons why we came to our conclusion about the environment was because we do typically see those dolomites in the nearshore, whereas a lot of our limestones directly overlying glacial deposits we thought was in probably a more distal offshore environment.
Oh,
Well,
it would-
let's see, I had a question here. I have a bunch of questions. I think what all you guys are working on, this is so amazing. Now you talked about the oxidation of state of the atmosphere, like great oxidation event preceding this snowball Earth. Throughout time, it seems that there are oxidation events that coincide with the start of this snowball. Maybe you can leave it, maybe you can help somebody who works in the atmosphere understand a little more of what you think your evidence shows for as what started the snowball in terms of oxidation, and then when it flipped and you had, did you have a hothouse environment, or was it just an environment that trapped and deposited carbonate and it wasn't a hothouse?
Yeah, so I think that firstly, to talk about the first part of your question there, I think that we're not talking about like 16% oxygen like we have today. Like some of this early oxygenation was probably, sub 1% atmospheric oxygen. And it was probably, I think, like a stepwise movement towards higher amounts of oxygen in the atmosphere. And then in terms of hothouse, I think some of that is supported by work I think that Phil has done, where he looks at viscosity of the oceans. And with different viscosities, you can actually determine sort of how hot or cold the ocean was. So I think closer to the Neoproterozoic, if I'm not mistaken, we did have really warm oceans. And again, that's also supported by whether or not we're seeing predominantly calcite or aragonite being precipitated. Aragonite will typically be precipitated under different conditions and warmer conditions than calcite. So you can use the precipitation of calcite or aragonite to tell you things about how warm the oceans were at the time, as well as sort of what the viscosity of the water was at that time.
So how warm was it when you had the trying to get all the Espanola deposit laid down? How warm was it compared to the Bruce Formation deposit?
That's a good question. I don't know. Warmer than 0 degrees Celsius, probably.
Oh, it's interesting. Well, and I'm sorry, one more question related to that. The role of methane emissions in there. Can you estimate with anything you've done how much methane came out? Like what was the role of methane in, say, a greenhouse event? And I realize the oxygen is important because, and weathering as well can, I got the experts in it, Paul can explain better than me, but to pull down and react with the methane so it won't stay a hothouse forever. But I'm just trying to understand, how could you get an estimate how much methane came off, and was it really significant for a climate factor?
Yeah, that's an interesting question. I don't know necessarily how much methane we had before and how much methane we had after. I don't. There's probably a bit of work done on that, and we could probably draw some more recent atmospheric work that's been done to make conclusions about that. As we know, again, like I said, with the melting of the methyl hydrates, this is a process that's going on still today. So these are things that in some ways we can draw modern proxies into the discussion. But in terms of how much of an influence it had back then, I'm not sure.
Well, your work just has lots of implications, because obviously if we harvest methane in the seafloor now, and are we going to, or if we warm up more, are we going to release that methane, and would it?
Undoubtedly, yeah.
Yeah, so what would its effects go? So I'm sure other people have questions. Are there any other people that want to speak out? And I would love to hear Paul's comments as well.
Yeah, Paul's the expert.
Coming to Mindy's question about the temperature, it might not be so important the absolute temperature as the temperature change. Because if it is warming, in other words, the temperature is rising, then that's going to drive up the saturation state of the ocean with respect to calcium carbonate. We all know that carbonate forms preferentially in the warmer parts of the surface ocean. So if you have a strong warming trend, that could help to explain the Espanola Formation, which is bound to be significant because it represents the only carbonate unit in the entire Huronian sequence. And when you go to Wyoming, it's the same story. There's only one carbonate unit, and it's the Wagner that's correlative with the Espanola. So this carbonate anomaly within the Huronian succession must be significant, and I'm delighted that the Bruce and the Espanola are receiving the attention which has formerly been attracted to the Galganda.
Well, if no one else has any questions, I'd like to thank Sophie for giving us a really interesting talk. Paul, I'd like to know where in Wyoming you see the Huronian
The Snowy Pass supergroup, and as the great Stu Roscoe pointed out, a great Canadian geologist who actually was one of the very first people to provide evidence for the great oxidation event through the disappearance of unstable detrital minerals like uraninite and pyrite in the lowest parts of the Huronian succession, which disappear upwards. Stu Roscoe, in many ways, is really the founding figure in the whole great oxidation event concept. And Stu Roscoe documented correlation between the Snowy Pass supergroup in Wyoming and the Huronian formation by formation. And subsequent work has only reinforced those correlations.
Okay, well, great. Well, Sophie, thank you very much. I've actually gotten organized to come up with some AWG swag to send you. We have these caps. So if you send me your mailing address, I'll send you this.
Thank you.
Great.
Thank you everyone for listening.
Yeah, it was terrific, and got to go look at those units sometime. And
Yeah.
and there's a lot of similarities to the deposits you're showing to what we can see in places in the Monachies, which are also quite old rocks. So it maybe in the future can get you to lead a AWG field trip with Paul or whoever on Snowball deposits.
Yeah, that'd be cool.
It's hard to beat the Sudbury area for spectacular geology of all sorts.
That's true. Very true.
Well, thank
And
you
very
very much.
accessible.
You just presented so well. Thank you so much.
Right.
Thank you so much, everyone. Have a good
We're going to
afternoon.
follow up with a social time for anybody who wants to stick around. The other thing I wanted to do before you leave is introduce Melanie Klim, who's our new Pacific Northwest chapter president. I'm now past president. Yay! So Melanie will probably be, running the next Zoom meeting, which should be in late January or early February, and our this year's Tanaka Scholarship recipient has agreed to give a talk, and so that will be Haskell White from Oregon State University. I'm not quite sure what she'll be speaking about, but she's agreed to give a talk. So
Yeah,
on to
thanks,
any
Marcia.
socializing anybody wants to do if you want to unmute yourself.
That's great. You've stopped the recording?
I will do that right now.